I come from the National Quantum Information Center in Gdańsk, Poland. And today I'm going to tell you about our recent work of emergence of classicality and objectivity in all causal theories. Okay? So this is a collaboration with Carlos Candolo, Jarek Korvich, and Professor Pavel Horodecki. And as you can see, this is a group I'm proud of being part, and I think we have like a good team for the adventure of research that all of us we take. Okay, so what I'm going to tell you today, first, what is the problem behind the quantum to classical transition? What are general probabilistic theories? I will go kind of like the details on the operational definitions that we have to understand GPTs. Why it's interesting to then study the transition to classicality in GPTs? What is our definition of generalized decoherence that suits for the purpose of our research? Then what is objectivity? What is this concept, this feature, in terms of a game? And then what is like the future research perspectives coming from the result that we get? And some final remarks. Okay, so what is the quantum to classical transition? Essentially, it's the question that how this classical world that we observe appears out of some quantum nature. How our fundamental theory can give rise to this phenomenology that we have some intuition about. Okay. You can imagine that you have your fundamental theory of nature, or quantum in this moment, which has very non-intuitive perspective. Usually what we do nowadays is we don't understand this, but we say that at least it's not something else. So we would like to understand how out of this emerges something that is more definite, something that the features that we are used to. Because if there's a fundament for our understanding of reality, it should also explain why we have these features. Key concept of this is interaction with the environment. And I will say that in this kind of works, we're trying to see it in a kind more fundamental way. So you can see as, for example, for James Bond, to define some character, to define even the personality of someone, it's an important part. What is the interaction with the environment? How the information that you spread define your relationships, for example. So this is very important for all the approaches in this understanding of emergence of classicality, where the first step were done by decoherence theory. Then later, more advances research was with quantum Darwinism, and other approach is this of objectivity, like the emergence of this property and broadcast structure. Quantum Darwinism is more analytic because it is based on some measures that relates the information between environment fractions and the system that is becoming classical. While this objectivity and broadcast structure is more geometric because it's it tries to define what is the structure where this classicality can happen. And then later compares the states or the other systems with this structure to say how much is the degree of classicality that it has. And we will try to extend, we will extend this notion to GPTs. Okay? So what is general probabilistic theories? There has been very good talks now that have presented some first glance about GPTs, yesterday with Sicard and now with Miguel. And you can say that this is a framework, some frame, in which you can see different theories that we have nowadays, in some equal perspectives. So you can say classical, quantum, and even beyond quantum can be put kind of on the same level of analysis. So it helps us to think about all these things all together. So what is the starting point when you look at this operationally? They have like two key elements, two blocks, constructing blocks, which are transformations and systems. Here in this kind of representation that I'm going to use, systems are wires, and transformation are these kind of boxes, but basically they represent some process that happens in some device. Okay? So basically all of these represent like devices that are interchanging physical systems. Yeah? So when you have some transformation that only has output, then you say this is a state. And when you have only input, this is an effect. So important concept is what is device, which is a collection of transformations. Yeah? And usually this is called in literalized test. But conceptually, it's like you have your device, and in this device can take place different possible transformations, maybe probabilistically. Okay? When you have some device that only has effects as these transformations, then you call this a measurement. So it's like a box where it's coming some system, and then suddenly one possible transformation takes place, and this is the effect, and this is the result of your measure. Okay? So when you have these devices happening, like connecting, interchanging these systems, then at some moment, some instance of this can have different transformations, yeah, observed. And this you can represent in some circuit-like form. Yeah. All these transformations may happen like with some probability in the devices. Yeah. And the theory, so the GPT, should tell us what is the joint probability distribution for this transformation to actually happen. Okay? So this is like the essential thing. So you have some devices, interchanging systems, that in some instances realize transformations, and your theory should tell you with which probability you will have this outcome. Okay? And then you have similar notations like in quantum, just to make it easier over life. Yeah? So for example, the probability of having this instance is represented here with this kind of bracket notation. If you have some transformation in the middle, it can be like this. Also, for GPT, it's important to talk about compositions, yeah, which can be in series or in parallel. And it's important to notice, as Sikar told us yesterday, that this tensor product not necessarily is the same tensor product that we talk in quantum mechanics, but it can have like very similar properties if you make some assumptions, let's say like local tomography. Okay? But in principle, it's just that you have the systems in parallel, like transformations applying to systems in parallel. Okay? And you also can talk about like things like measure and prepare in this form. Okay? So additional concept is necessary to understand our results is, for example, concept of refinement. So if you have some test A in some device and some test B in other device, applying that can be applied to the same system, if the test B can be written in terms of decomposition of rearrangement of the transformations of E, like for example you can see in this partition, then you say that A is a refinement of B. Yep. Which means that it's giving you some more fine information. Yep. And refinement can allow us to talk about purity. So in particular, transformation you say is pure if only accept trivial refinement, which is basically adding some probability distribution in the front. If the transformation is not pure, then you say it is mixed. Okay? Other concept that is important is distinguishability. So if you have a set of states, you will say that they are distinguishable if there is some measurement that can singles them out in one shot. So they come to your device with the measurement, and the measurement will tell you which is the state. If you cannot add any other state, then you say that this set is maximally distinguishable. Okay? And a channel, finally, is a deterministic transformation, which also you can say is like conceptually like a device that has only one possible process, only one possible transformation. So you are sure that this is what is going to happen to the system. Okay? And here is our first assumption, which is like quite like natural and used in GPTs, and this is causality, which says that if you have your device, any measurement, any test that you can apply on the output of this device does not affect the probability that some transformation will happen in your device. So it's putting some time order in the processes, and that you will not get influence from the future to the past. Okay? And there is many different formulations, mathematical, but one of them is like this. So if you have there is other equivalent. So if you apply some measurement on some state, the probability that something will happen, yeah, it doesn't depend of the measurement that you are doing on this on the system that is output by this state. Other equivalent form is the existence of this throwaway or deterministic measurement, which Sikar talked yesterday. And basically, it turns out that this part is equal to this U. Okay? So when you have this operational framework and you are assuming causality, then you have this nice convex representation of the states. Yeah? So let's say you have the space of states for some system A, and then you will represent it in terms of this convex set, this cone. Yeah? Where here in the surface are the states which are normalized, and below are subnormalized. Yeah? And from the functionals, a subset of the functionals that will take this cone into probabilities, yeah, is the set of effects of your theory. Yeah? So you have two cones. One is for the states, and other for the effects. Okay? All of this comes once you have assumed causality. Okay? So then we can talk about classical theory, because this is what we want to reach. Yeah? First, we have to define what is a classical set. So we will say that a classical set is you have a maximally distinguishable set of pure states. Yeah? This, and then you take the convex hull of them. And then this, together with the effect cone, yeah, it will be like your classical theory, yeah? Some classical subtheory. And here you have some examples of convex set that can be described in some subclassical theory of your GPT. And here comes some question. Is this always possible to have a classical subtheory? What do you think? Is it always possible in any GPT, even assuming causality? Okay, I tell you, no. So there is some weird creatures in GPTs where you will never have, that are well defined, but still you will never have like a subclassical theory. And this was one of our contributions to have one of these examples. So we call it the restricted Trit, and basically the state space is the same as some tripartite or classical state. No, okay, no, not tripartite, but with some Trit state, classical. But the space of effects is restricted. So only this blue part of the space is allowed. Okay? And you have to be careful when constructing this counterexample, because you don't want to have like some theory that doesn't have classical state because it's kind of incomplete or faulty. This is like kind of proper theory because the state and the space of effects is like linearly independent, and with them you can do tomography. So with this, you can do the tomography of the space of states. Okay? It has like the same dimension. No? So, but you will never have a measurement that will do the single shot distinguishability of the maximally pure, maximally distinguishable pure states of the theory. Okay? So in this kind of theory, you never have like classical subtheory. Okay? And this is our first result. So then this brings to us like some additional, yeah? Yeah. Exactly, exactly, yes. But, and this is the point, okay? So, see, this is a very good point. So, when you are doing this operational, you are assuming that at some moment, at some level, you are having classical theory. So, it's very weird if you have some theory that you claim to be fundamental, and out of this never appears some classical theory. So, in this case, you will have some theory that is describing some phenomenology. This probably is like you have some faulty devices for measuring, okay? But, and then you know that you have classical theory, but out of this, it will never appear. So then you cannot say that this is fundamental theory of nature, okay? So this is our point. Yes, this is very good point, okay? So it's like also some test of kind of self-consistency if you want to say that your GPT is fundamental. And that's why we claim this as some principle. Yeah? And that the classical concept has to be able to emerge, not only to postulate, but to emerge, yeah, of the theory. And yeah, so any classical concept should, as any theory has to have some classical set or arbitrarily close approximation of this, or otherwise you can say it is a GPT but not fundamental. Okay? So now, what is our concept of decoherence? Yeah. First, I have to say that there is some other works with decoherence in GPTs, but basically there the idea was to talk about like decoherence and how natural assumptions about decoherence may rule out some other possible theories. But in our case, we want to focus on the classical features that will emerge. Okay? So then we want to take like the minimal assumptions about a decoherence. So we will take some more minimalistic definitions, so less assumptions. Okay? I'm not saying that these are wrong. I'm just saying that they are built for different purposes. So they may have some reasons to say, oh, this is a good feature for a decoherence, it's satisfied by classical or and by quantum, but how do you say, they are not necessarily for our purpose. Okay? Okay? So what we will call a complete decoherence, it will be some channel, so deterministic transformation, that will bring any states from your GPT into some classical set. Okay? So this is the first condition. And the second is that if you have some state that is already in this classical state, it should leave it invariant. Yeah? So it will have like some symmetry. Okay? And we were able to prove that in any causal theory, there is always one of these complete decoherence, and it's given by this kind of channels, like prepare and measure. Yeah. Okay. Now we have like the elements, yeah, to talk about like with this concept of objectivity, and I'm putting in terms of some game. Okay. So the basic structure is like this. You have James Bond that is going to play some card game against his, okay, he's playing in some casino, and some of his more deadly enemies wants to know what is the result of his card. Yeah? And they have some screen in their labs. Yeah? So they represent like environment, that is getting information out of the system. But in order to say that this result of James Bond is kind of objective, it should happen that the results that must be correlated with this of each one of them. Yeah, you see, yeah, of the results of their measurement on their states, and they should agree. That there is this sense of agreement. So when you see some system and you see some property, let's say the color of the blackboard, yeah, and all of us agree about this, this gives us this sense of objectivity of this color. Yeah. Other property that is important is that when we are all seeing this, it should not change. So the process of measuring this should not change this property that we are claiming to be objective. Yeah? It's not this objectivity in the philosophical sense. This is more about like kind of phenomenology that gives us this idea. The conditions in more formal sense will be like non-disturbance. So this row will be kind of the multipartite state of all the people that is involved. So the central state that is going to be objectified, and the states of the environment. Yeah? So by the process of the measurement of each of the parties, the whole state should keep invariant. And this is the condition that is called non-disturbance or Bohr non-disturbance. Yeah? And the other condition is this agreement that I was explaining, such that there has to be this perfect correlation between what is the results of the environment, or the states of the environment, and the state that is measured, yeah, and decohered by the central system. Yeah. Other important conditions that we include is this strong independence, which says that these environments, yeah, that are getting the information from the central system are in the only correlation they have is through the system. So they are not communicating themselves. You can say these bad guys don't like each other. They don't like, the only common things that they don't like James Bond. Okay? And this is more like a technical condition that it doesn't affect the fact that we want to objectify the central state, yeah, to find a structure where the central state is objectified, but make it easier our work. Okay? There is some works of people in the quantum case where it's trying to get rid of this condition, but in the original work it was also assumed. So we give you this because this is first work on this in GPTs. And the other thing is important is like in this sense of for having this phenomenology of objectivity is that you would like these measurements to be repeatable. Yeah? So that the people, when they are looking at this, let's say object, let's say the green screen, they will say, okay, but I want to look at the game, and they will see the same. Okay. So, and then that's why we define these sharply repeatable measurements, and we will say this is the kind of transformation that each of the environments apply. Okay. So, and then the other element to understand this result is this spectrum broadcast structure. Yeah? This is like the generalization of a spectrum broadcast structure to GPTs, in which you have basically some convex combination of the parallel of the states that have this perfect correlation together. Okay, and these centers are pure and perfectly distinguishable, and all the others are distinguishable. Okay, so this was the main structure used to characterize this objectivity in quantum, and we generalized it to GPTs. Okay, so what are the main results? Basically, that spectrum broadcast implies this phenomenology. So when the states on this structure have this broadcast structure, then you are sure that they will experience this phenomenology of objectivity. And on the other way, if the people is with their measurement seeing this phenomenology of objectivity, and additionally you have this strong independence between the environments, then the only possibility is that the system is in this kind of state, broadcast state. Yeah. The first part is like more easy, and basically the broadcast structure was made to satisfy this, but the converse is the not trivial, and the biggest achievement in this first work on here is that we were able to do this only assuming causality and the existence of some subclassical theory. While in the original work, you have to use the full structure of quantum mechanics to prove this. Okay, so this gives like some background for some research program or some research line in GPTs. Yeah? So then you, for example, you can start looking at what is like the distance from some spectrum broadcast structure in your GPTs, and then gives this some will be kind of measure of how much close to having objectivity or classicality your state has in the GPT. You can look for extending to continuous variables. You can now ask, is it this, can we extend also quantum Darwinism? This is like more difficult question because we know that in GPTs there is problem in defining like mutual information, and this is based on that. But maybe there will be some other ways, maybe applying some of the tools that we have studied here in this conference from SDPs, so maximizing some quantity. Yeah. What is happening with the emergence of other classical features? And this is something we are already very interested in and thinking in some other possibilities, yeah, and which are more practical to extend to GPTs. Is it generic the emergence of classical features in every GPT? This is other question, like for example, there is a well-known work by Brandao about the generic emergence of classical features in quantum Darwinism. So it's not only the question if the classical can appear, but it appears generically, so there is a high probability that classical work will appear, because maybe your theory has classical sub-theories, but maybe the probability that this will happen is very low. So then also it will be less likely to be like the theory that will describe nature. Okay? And is the interaction with the environment something that defines quantum? So here we are opening like many questions. So for example, if looking at one of these particular features, classical features, maybe the ratio in which this appears for quantum is different than for other theories, and this tells you something about quantum. Yeah? But the main message for you, yeah, is that this is a new topic, new research area, like where in GPTs, where naturally the problems relating convex sets will appear very much in similar way as Sikar showed us yesterday with these cryptographic problems. Yeah? This is also some area where convex methodologies, convex analysis could be applied like natural. Okay? And actually, in some of the ongoing research that we are having, looking at this, for example, emergence of other classical features, we're finding problems where we should apply some SDPs or convex optimization. But this is like, it's kind of trivial, but the kind of things. But of course, it's a reason why I also wanted to come to this part of conference, because I see that I would like to learn from these tools, because I'm seeing that if we want to push forward this research, it will be useful. Okay? So finally, what I have told you first, I have shown you that there is existence of these theories without classical states, and that's why we say that they are not fundamental, for the reason that we discussed with Miguel. And actually that we have this spectrum broadcast structure, like we show that it can be used to characterize any objectivity in causal GPTs, which claim to be fundamental. Yeah? And also we have some other additional results in our work, like related to axiom for the locality of observers too. This has more to do with that we would like to have some heuristic properties in the environment. Yeah? There is this will be some other reasons to rule out GPTs for having some behaviors that in this emergence of classicality or experience classicality will not be likely. But I didn't want to go further because it's separated from the objectivity of the central system. Okay, this is more about some other global properties that has to do with the environment, which is looking at the system. Right? Here I wanted just to focus on the objectivity, and for that we just needed the causality and the existence of subclassical theories. Okay. So thank you very much, and you can find all this work in this archive. Mm-hmm. Mm-hmm.